Hello everyone, I am Paritika Kayal from University of Toronto, and today I am going to talk about our work on deployment of distributed IoT applications in fog computing environment using Kubernetes as an orchestration tool. So in this presentation, I will first introduce the fog computing model and Kubernetes architecture. Despite the progress made by academia and industry with respect to container management and wide-scale acceptance of Kubernetes in cloud environments, container management in fog environment is still in the early stage in terms of research and practical deployment. So in this paper, we demonstrate the practical feasibility and practicality of deploying and managing containerized IoT applications on real devices. So first, let's see what a fog network is. A fog network consists of fog nodes, which are computational networking, storage, and acceleration devices. Figure depicts a network of 4 fog nodes. Edges between the fog nodes indicate communication links, with edge weights indicating the distance between the nodes. These fog nodes are resource constrained and cooperate with forwarding data. Now, what a fog application is. So by adopting microservice architecture, fog applications are designed as a collection of independent and loosely coupled modular services called microservices. These microservices are installed in lightweight portable runtime environment called application containers. So the figure below shows an example of fog application consisting of 5 microservices. Directed edges indicate the direction of communication, and edge weights shows the amount of data flow between microservices, which is referred as chaining degree. Now, a crucial component in fog computing is the placement of fog applications on a fog network. This determines the overall system performance in terms of energy consumption, communication cost, load balancing, and others. Placement of microservices can be done in two ways, which represents a trade-off between two placement objectives. So the first strategy is to place the maximal communicating microservices on a single fog node. This keeps the chaining cost between the microservices low, but at the same time, it leads to high utilization on some of the fog nodes. Also, this strategy may not be feasible because of the limited resources at fog nodes. So the second strategy is to split the microservices over the network. So this leads to data exchange between the microservices over the network, which contributes to network delay. This strategy results in a load balance system, but at the same time increases the network delay. We want low energy consumption at fog nodes and low network delay of the application. So these dual objectives presents a trade-off. And thus, the distribution and management of IoT applications requires an efficient orchestration tool. So towards this and Kubernetes is a Google incubated open source container orchestration tool. It has been widely used in cloud computing environment. So Kubernetes follows a master slave type of architecture. The master node initializes and manages the cluster, and it is the entry point for all administrative tasks. It consists of components like controller, API server, and scheduler. The worker nodes then join the cluster and are controlled by the master node. So Kubernetes nodes are physical devices running services like Docker, which provides a container runtime, and Kubelet, which executes containers on the node as dictated by the master node. The main basic and control management unit of a Kubernetes is a pod. So in this figure, the circles are indicating the pods deployed on the worker nodes. So pod is defined as a YAML file which consists of the reference of one or more Docker images which are pulled from the Docker registry. So let's see how the application deployment in cloud works. So first, the user sends a kubectl command to create a pod on the Kubernetes node. This request is sent to the master API server. The scheduler and master node watch for the newly created pod and bind the pod to one of the worker nodes that satisfies the pod requirement. The API server writes this binding to the database, and then the kubelet at the worker node watch for the binding and start running the pod. This status of this running pod is then updated to the master node. But due to the distributed nature, heterogeneity, and limited resources of fog nodes, fog computing environment have different orchestration requirements, and the analysis of performance and usability of Kubernetes in the fog computing environment is an interesting and relatively new area of research. So in this paper, we demonstrate the industrial feasibility and practicality of deploying and managing containerized IoT applications on real devices. So the design is implemented on a network of 4 Raspberry Pis acting as fog devices and one PC that serves as a master node. So we used Ubuntu as the operating system and installed Kubernetes and Docker engine on each device. And we used VNet as container network interface plugin to enable overlay tunneling between the fog nodes. For creating live streaming IoT application, we used Node.js and Motion software. Multi-platform Docker images for these IoT application containers is created using Docker BuildX CLI plugin and pushed on the Docker Hub repository. So with this set of hardware and software, we achieve a placement as shown in the figure, where all the communicating microservices of the application are placed in a single Kubernetes pod so that they can communicate with each other on localhost without any communication delay. So we observe the time lag in this situation as the video stream travels from container 1 to container 5 through using 2 different paths as shown in the figure. Next, we deploy the containers of the application distributed over the network so that they need to communicate over the network to achieve the application functionality. Here we can see that each container is placed on a different Raspberry Pi is deployed in a different pod and they communicate over the network. So in this case, we observe that the time delay and the video quality achieved at container 5, the result shows that a greater time lag as compared to the first scenario. Here, every pod has a different IP address, and in this case, we need to enable networking between these two pods on different fog nodes. So in order to enable networking between the pods, we use VNet as a overlay tunneling. We use VNet overlay tunneling, which stores routing table for communication between the nodes in the Kubernetes cluster, as shown in figure. So with this, we were able to achieve the overlay tunneling between the two pods, which have different IP addresses present on the different fog nodes. So with this, I conclude. Through this demo, we show the applicability of Kubernetes for deploying IoT applications in fog computing environment. We observe that in the two scenarios, the application functionalities can be kept intact. We also observe that there is a time lag experienced by the application when the application is split over multiple fog devices. Thank you.